Alright, this video is about gases. So we know some facts about the different states of matter. Solids have a certain shape, and they do not flow, and they are not compressible. So if you have a beaker that contains a solid, the solid will have a definite shape, and it contains particles that are very organized in the structure. Now, if you have a liquid, the liquid will take the shape of the container. So here it's going to fill in, and it can flow, so you can pour it. There's more randomness to the particles. It's a little bit compressible, not really measurable. And then you have your gases. I'm going to put a lid on this. So the gases will actually take the shape of the container, and you can compress them because they're full of all these empty spaces. You can compress them, and they can flow as well. Kinetic molecular theory. So particles are always moving. The only time we don't have movement is at absolute zero. So the types of motion and degree of motion depend on the state of the substance and the strength of the attractive forces between the particles. So if we have vibrational motion, so this is my particle, it will vibrate in place. It will shake, and all particles can do this. Rotational. If the particle has rotational energy, it can roll, it can rotate in its place. Translational motion, it means it can travel in straight lines. So solids have the strongest forces of attraction, and gases have the least, which is why the solids have the least degrees of motion, and gases have the most. So gases can have vibrational, rotational, and translational, but solids have vibrational. As the substance is heated, the kinetic energy of the particle increases, and the temperature of the substances increase. If there's enough kinetic energy, the particles can change state as the attractive forces between them can be overcome. Temperature is a measure of the average kinetic energy of the particles. Gases will maximize the space between the particles and will spread to fill an entire container. They are easily compressible due to these large spaces. Gas laws will take into account 4 different variables. Pressure, it's usually measured in kilopascals or atmospheres, but it could be millimeter torr, it could be millimeters of mercury. The temperature is in kelvins. It's not going to be measured for gas laws in degrees Celsius. You always have to convert it to kelvins because you can have 0 degrees Celsius, which messes up your math. Amount is also involved, which is of course moles, and volume in liters. Now, one definition you need to understand, and that's pressure. When we're talking gas pressure, pressure is the force of the gas particles colliding with the walls of the container. So pressure is the force of the gas particles colliding with the walls of the container. So the more particles you have hitting the container walls, the higher the pressure. So we're going to look at 4 gas laws in this lesson, and there'll be another video afterwards. But these 4 gas laws involve 2 sets of conditions. A set of conditions prior to a change and then after the change. So Boyle's gas law. Basically, Boyle's gas law states that pressure varies inversely proportional to the volume when temperature and the amount of substance are kept constant. So there's 4 variables: pressure, temperature, amount, and volume. And when we see the effect of varying 2 of them, we have to keep the other 2 constant. So if we're going to test pressure and volume relationship, temperature and amount have to stay constant. So pressure varies inversely proportional to volume. So basically, if we have a container with a piston, and we have gas particles in here. Well, if we depress that piston so that the volume is smaller, the particles are going to be much closer together and are going to be colliding with each other more and with the walls of the container more. So when you decrease the volume, the pressure will go up. So we can write this in a formula: P1V1 equals P2V2. So the pressure times the volume will equal some constant. So therefore, a set of conditions, i.e. 1, will be equal to the set of conditions at a different time if the amount and the temperature are kept constant. So a 2-liter helium balloon is at an atmospheric pressure of 101.325 kilopascals. It's accidentally released, flies up to a level where the atmospheric pressure is now 98 kilopascals. What is the new volume? So this is our situation before. We had a volume and a pressure. Now we have a new pressure and we want to know the new volume. So 2.0 liters times 101.325 kilopascals is equal to 98 kilopascals times the volume. So if we divide both sides by 98 kilopascals, we will end up with our new volume. Now our pressure decreased, so it makes sense that our volume, because they're inversely proportional, if our pressure decreased, our volume should increase. So our second volume is 2.07 liters, which is basically 2.1 liters, rounded off to 2 sig figs. So we have increased the size of the balloon. If it goes up even higher, it could eventually explode. So this is Boyle's law, and you would use this formula. Charles's law. So the volume will vary directly with a change in temperature when pressure and the amount of substance are kept constant. So if you ride a bicycle regularly, you might notice that your tires seem to go a little bit flat in the fall, and that's because the temperature has cooled down, so the volume in the tires has cooled down even though the amount of gas is the same. So in this case, this is our formula. Again, it's a type of problem where there's two sets of conditions. There's a before and after a change. So you're always going to be given enough information. You'll have three pieces. You'll have to find the fourth. So a gas has a volume of 0.250 liters at 25 degrees Celsius. We have to change that to Kelvin. So if you add 273, you get your temperature in kelvins. What would be the volume if the temperature is increased to 65 degrees Celsius? Again, change this temperature to Kelvin by adding 273, and that's 338 Kelvin. So we've got temperature 1 and temperature 2. So V1 over T1 is equal to V2 over T2. What I strongly suggest you do before you plug in any numbers is rearrange so you can solve for your unknown. We would multiply both sides by T2 to solve for V2. So V2 is equal to V1 times T2 over T1. So 0.250 liters times 338 kelvins divided by 298 kelvins, and this is 0.280 liters. So our temperature increased, so our volume increased because they vary directly. If you increase the temperature, the volume will go up, and if you decrease the temperature, the volume will go down. And this is if pressure and the amount of gas are kept constant. Gay-Lussac's law. Pressure varies directly with temperature. So that means that if you increase the temperature, you increase the pressure. And that's because when you increase the temperature, the particles have greater kinetic energy, so they're bouncing into each other in the walls of the container with greater frequency, so the pressure goes up. A sample of gas is stored in a rigid stainless steel container, so we know volume's kept constant. And we also have to keep the amount of gas constant. So it's stored at negative 120 degrees Celsius. Change that to Kelvin. So minus 120 plus 273 is 153 Kelvin. And a pressure of 41.2 kilopascals. If the pressure is increased to 65.5 kilopascals, what's the temperature of the gas in degrees Celsius? So again, rearrange your formula first before you put in your values. So we want to find T2. So to isolate T2, we're going to multiply both sides. And then to isolate T1, we're going to multiply, to isolate T2, we're going to multiply by T1, divide by P1. So T1 over P1. So T2 is equal to P2 times T1 over P1. Now substitute in your values. P2 is 65.5 kilopascals. Temperature 1 was 153 Kelvin. And the second pressure was, the first pressure was 41.2 kilopascals. So kPa cancels. So when you do the math, you end up with 243.2 kelvins. Subtract from that 273 kelvins and you have degrees Celsius. So negative 29.8. So the temperature rose from minus 120 to minus 29.8, and the pressure also increased from 41.2 to 65.5. So temperature and pressure vary directly. Increase in one requires an increase in the other. Combined gas laws. It's called combined gas laws because it takes the three previous laws and combines them. So you can use this formula if you're only keeping your amount, your number of moles of gas constant. So a sample of gas has a volume of 30.0 liters at 125 kilopascals and 25 degrees Celsius or 298 Kelvin. What is the volume, so we're looking for V2, of the gas at STP? Well, where's the second pressure? Where's the second temperature? Well, it's actually given in this acronym STP. STP stands for Standard Temperature and Pressure. So 0 degrees, 273 Kelvin, and 101.325 kilopascals. SATP is Standard Ambient Temperature and Pressure. So 25 degrees Celsius or 298 Kelvin and 100 kilopascals. So our temperature is 0 degrees Celsius or 273 kelvins, and our second pressure is 101.325 kilopascals. So now we have our set of conditions. P1 V1 over T1 equals P2 V2 over T2. We want to find the volume of the second condition, so we're going to multiply both sides by T2. And divide both sides by P2. That way P2 and T2 cancel, and you have V2 all by itself. So V2 is now equal to P1 V1 T2 over T1 times P2. So now substitute in your values. So 125 kilopascals times 30 liters times T2, which is 273, divided by 298 times 101.325 kilopascals. So this is equal to 33.9 liters. So initially the volume was 30 liters, and after the change, we changed the temperature, we changed the pressure, we have a new volume, and that is 33.9 liters. So we've got Boyle's law, Charles's law, Gay-Lussac's law, and combined gas law. So the next law we're going to talk about is the ideal gas law, and it also has a formula, but it deals with one set of conditions, not two, so it's not an equal to formula, like as in same on the left, same on the right. However, we can use it to find all the formulas for these four gas laws.